flat steel coil is about to become a duct capable of moving air through an entire building. The strip enters a spiral-forming machine where rollers curve it continuously and lock the edges into a helical seam. That spiral joint also acts like a reinforcing rib, allowing thin galvanized steel to stay round and resist vibration without adding unnecessary weight. For larger straight ducts, a wide sheet passes through powered rollers and gradually bends into a cylinder. The operator must feed both sides evenly. Even a small misalignment can twist the tube and prevent the edges from meeting correctly. Galvanized steel is used because its zinc coating helps slow corrosion in humid ventilation systems. The next machines produce curved elbow fittings. Short cylindrical sections are clamped in a rotating fixture while shaping tools form beads, flanges, and locking edges around each end. Several angled sections are joined to create one smooth bend. This segmented design lets air change direction more gradually, reducing turbulence and pressure loss compared with a sharp corner. Tight seams are equally important because leaking joints waste fan power. Now the scale increases dramatically. Workers guide a much wider sheet through heavy rollers to form a giant circular shell. A hand wheel adjusts the roller gap and controls how tightly the metal curves. Because the sheet is thin relative to its size, several workers support it at once. This prevents sagging, creasing, and misalignment. Once the edges meet, the seam is secured and the large sections are fitted together. The factory then switches to flexible ducting. A coated fabric strip is wound around a rotating form, while a spiral wire is trapped inside the wall. The wire prevents the airway from collapsing, while the flexible skin allows the duct to bend around beams and equipment. The completed tube is inspected, compressed, and packed into a small box, then expanded again during installation. A second flexible design uses an extremely thin metallic film. The material is wrapped helically around a reinforcing structure, creating a lightweight reflective tube. The operator maintains steady tension because uneven overlap can create weak points. Although the film looks delicate, the spiral construction spreads bending forces along the duct instead of concentrating them in one area. For heating and air conditioning systems, the flexible core receives a thick, fibrous insulation blanket. This layer slows heat transfer, helping conditioned air maintain its temperature. A reflective outer jacket is then wrapped around the insulation. It protects the fibers, limits moisture penetration, and helps reduce condensation on cold ducts. Finally, the tube is sealed, compressed, and boxed, ready for installation. These heavy-duty work boots are not simply glued onto a rubber sole. The craftsman first coats the lug outsole with adhesive, then carefully aligns it beneath the leather midsole. This rubber compound is chosen for its resistance to abrasion and its deep tread, which provides grip on mud, gravel, and uneven construction sites. Precise positioning is essential because an off-center sole would affect both balance and appearance. The excess rubber is removed with knives and rotating trimming tools until the outsole follows the shape of the boot. The craftsman constantly changes the angle of the boot, allowing the blade to work close to the leather without damaging it. A heavy sole stitching machine then drives thick thread through the outsole and the layers above it. Adhesive provides an even bond, while the stitching creates a mechanical connection that remains secure even after years of repeated flexing. Attention now shifts to the heel. Adhesive is applied to both the rear section of the sole and a thick leather heel lift. Coating both surfaces creates a stronger contact bond once the layers are pressed together. The heel is built from dense leather because it can support body weight while still being shaped and repaired. After alignment, repeated hammer strikes force out small gaps and seat the layer firmly against the boot. The heel cap is secured with both hammer pressure and metal fasteners. A small setting tool drives each fastener below the surface of the tread. Recessing the heads prevents them from touching the ground, where exposed metal could reduce traction or become damaged. The craftsman must also avoid driving them too deeply, which could weaken the rubber around each hole. The leather upper is polished against a rotating wheel. Friction spreads wax across the surface and gently warms it, helping the treatment enter the leather rather than remaining as a dull layer on top. This process restores a richer color, smooths small handling marks, and adds limited protection against dirt and moisture. Curved sections around the toe and ankle require especially controlled movements. Additional fasteners reinforce the heel from below, where walking produces repeated impact and twisting forces. A fresh layer of dressing is then brushed onto the leather to nourish areas that may have dried during assembly. The boot returns to the polishing wheels for its final finish. Different wheel shapes allow the craftsman to reach the heel, edges, and narrow curves that automated equipment might miss. After trimming, stitching, hammering, sanding, and polishing, the finished boots are finally revealed. Beneath the clean leather exterior is a structure designed to be worn hard, repaired when necessary, and kept in service for years. This transparent cylinder will eventually contain thousands of microscopic filters capable of cleaning blood. The process begins with clear housings, end caps, and small connectors produced from medical-grade polymers. Robotic arms inspect and transfer the components, while vibratory feeders arrange randomly piled parts into the correct orientation. Automation is essential here because every opening and sealing surface must remain consistent. The transparent material also allows technicians to inspect the blood path and detect air or contamination during use. Bundles of extremely fine hollow fibers are prepared for the dialyzer. Each fiber contains a microscopic channel surrounded by a semi-permeable membrane. During treatment, blood flows through these fibers, while dialysis fluid passes around them. Waste substances and excess water can cross the membrane, while blood cells and larger components remain inside. The fiber bundles are inserted into transparent housings, and automatic feeders supply the circular sealing components. Each part is pressed into position with controlled force, so the delicate fibers are not crushed. A precisely measured sealing compound locks the fibers at both ends. Controlled rotation helps distribute this material evenly, creating a barrier between the blood flowing inside the fibers and the dialysis fluid circulating outside them. After the sealing material hardens, the fiber ends are finished, so thousands of individual channels remain open. Red headers and sealing rings are then pressed and rotated onto the cartridge. The completed dialyzers enter a multi-station testing system. Tubes and fixtures check the internal pathways for leakage and consistent flow. Even a very small sealing defect could prevent the two fluid circuits from remaining properly separated. Production now shifts to the disposable blood tubing sets. Long transparent tubes are guided through green fixtures, measured, cut, and fitted with clamps and connectors. The red and blue components help medical staff distinguish different sections of the circuit during setup. Exact tube length and internal diameter are important because the dialysis machine uses them to control blood flow and monitor pressure accurately. Workers coil the completed tubing without creating sharp bends that could restrict flow. Each set is placed inside a printed pouch and heat-sealed. The closed packaging keeps the connectors organized and protected, while also preparing the product for sterilization, storage, and transportation. During the demonstration, a section of tubing is placed around the machine's roller pump. The rotating rollers move blood by repeatedly compressing the tube from the outside, so the mechanical pump never contacts the blood directly. The monitoring chambers are secured in their holders, and the tubing is connected to the dialyzer to create a closed circulation path. Finished products are packed into labeled cartons and stacked on pallets for distribution. Behind every box is a carefully controlled system of hollow fibers, tubing, seals, and connectors, designed to work together with extreme precision. These discarded metal castings are about to return as high-quality automotive components. A powerful electromagnet lifts the ferrous scrap and drops it directly into the melting furnace. Magnetic handling moves large quantities quickly while keeping workers away from sharp and heavy pieces. Using recycled metal also reduces the need for newly produced raw material, but the scrap must first be melted into a uniform alloy. Inside the furnace, intense heat turns the mixed scrap into a glowing liquid. The covered melting chamber helps retain heat and limits unnecessary energy loss. Before casting begins, the molten metal must reach the correct temperature and composition. If it is too cool, it may solidify before filling the mold. Excessive heat can increase oxidation and damage the mold material. The furnace tilts and transfers the molten metal into a pouring ladle. Workers skim impurities from the surface because floating slag could enter the mold and leave weak areas inside the finished casting. At the same time, shaped sand cores are positioned inside the molds. These fragile inserts create internal passages and cavities that would be impossible to machine economically from a solid block. The ladle moves along the molding line, delivering a controlled amount of metal into each opening. A steady stream is important because interrupted pouring can trap air or create cold joints where two partially solidified flows meet. Automation also keeps the filling time consistent, allowing every mold to receive metal at nearly the same temperature. The rough castings travel across conveyors and through rotating drums. Repeated tumbling removes loose sand and knocks away smaller fragments left from the molding process. These parts may look unfinished, but their complicated shapes were created in a single pour. This is why sand casting is useful for automotive housings that require curved walls, mounting points, and internal channels. The factory carefully recovers the remaining metal. Cut-off runners, rejected castings, and other usable pieces are collected and returned to the scrap area. An electromagnet lifts them back into the recycling system, creating a closed production loop. Instead of becoming waste, much of this material can be melted again to produce another batch of components. Each casting is then held against a large grinding wheel. The operator removes sharp flash, leftover gate marks, and excess metal from areas where the mold sections join. This work demands steady control. Grinding too little leaves an uneven surface, while removing too much could alter a mounting face or weaken a critical section. The parts enter a blasting machine, where fast-moving abrasive particles strip away burnt sand, oxide, and surface scale. This produces a cleaner, more uniform finish and makes cracks or casting defects easier to identify. After final inspection and sorting, the completed automotive castings are stored in metal racks, ready for machining and assembly. A simple coil of steel wire is about to become a tire chain strong enough to grip through snow, mud, and loose ground. The wire is pulled into an automatic forming machine, where it is measured, cut, and bent around the previous length. Every new ring must pass through the one before it. Even a small error in wire length would leave the ends misaligned and weaken the joint that will later carry the vehicle's weight. The unfinished links enter a resistance welding machine. Powerful electrodes clamp the two ends together and send current through the joint, producing intense heat exactly where the metal must fuse. Pressure forces the softened ends into one solid connection. This localized process is fast and avoids heating the entire chain. The welded links are then cooled and carried toward the next forming station. The continuous chain passes through rotating wheels and shaping tools that correct the pitch and orientation of each link. For tire chains, consistent spacing is essential because every cross-section must sit evenly across the tread. A worker then checks the chain by hand, using a jig and small hammer to correct links that are slightly twisted or out of line. Human inspection can detect irregular movement that automatic equipment may miss. Short cross-chain sections are now arranged between two longer side chains. The worker counts the links carefully, so every gripping section is positioned at the correct interval around the tire. Open connector links join the separate sections together. Pliers and a powered press close these connectors, while another welding operation permanently seals the joint. A loose connection could allow the chain to separate under impact. The assembled chain enters a continuous heat treatment furnace and gradually becomes red hot. Heating changes the internal structure of the steel, preparing it for higher strength and wear resistance. As the glowing chain leaves the furnace, it is rapidly cooled. The temperature and cooling rate must remain controlled, because excessive hardness could make the links brittle, while insufficient treatment would allow them to stretch and wear quickly. The cooled chains move up a conveyor and fall into perforated metal baskets. These openings allow liquid and loose residue from the previous treatment to drain away. The baskets are placed inside rotating equipment that helps remove remaining fluid from the tightly tangled links. Preparing a clean, evenly drained batch makes the following treatment more consistent. Larger batches are heated inside a pit furnace and transferred into a liquid quench bath. The heating and cooling schedule must be controlled to improve hardness without making the links too brittle. Workers finally separate and inspect the chains before fitting one around a construction tire, where the crosslinks provide extra grip on snow, mud, and unstable ground. From giant air ducts and handmade work boots to dialysis equipment, recycled auto parts, and heavy-duty tire chains, every process reveals the same truth. Reliable products are built through precise machines, carefully chosen materials, and skilled human hands. Which factory process impressed you the most? Share your answer in the comments and subscribe to Mr. Mechora for more powerful machines, satisfying production lines, and incredible manufacturing technology.